Hello, welcome to today's lecture on GPU programming model. We are going to understand in some detail how we can write programs for the GPU, which really means formulating our computation in a parallel manner. Since GPU is an accelerator and we are doing high performance computing, we'll care a lot about performance. We'll write CUDA programs and optimize them. Along the way, we'll gain a much deeper understanding of the GPU execution model and its memory system. So the reason why we are going through the process of writing programs for the GPU is because it's an excellent lens to understand systems aspect in machine learning workloads in more detail. So by going through this, we understand we will be able to get a clearer idea about the challenges that arise when doing training and inference on LLMs. And a lot of proposed innovations which are going to come up soon, like optimized attention or efficient parallelization of LLM across multiple GPUs, or even quantization techniques. Without this deeper understanding of the execution model of GPU, they might seem like abstract magic. So this lecture is really a bridge between the hardware architecture, which we discussed in the last lecture, and what's going to come later on in terms of techniques to improve LLM performance. When a case arises when we see that the GPU is underutilized, we turn to the profiler. Now the profiler returns a lot of data and a bunch of statistics. To be able to understand that, it's much helpful if we actually understand what a GPU program looks like and how it gets executed, and also about the memory hierarchy. And also a brief understanding of what a kernel is doing. It will help us appreciate later on when we talk about ML compilers. So it will help us understand what actually the ML compilers are optimizing for. Finally, PyTorch sometimes makes assumptions that are not accurate enough for us, or maybe it's not flexible enough for what we want to implement to address GPU bottlenecks. And then there's a need to be able to write CUDA kernel for a specific use case. So CUDA is a runtime environment to launch computation on the GPU. It's also a programming language extension. Specifically, it introduces some additional things to C++, and these take the form of mostly annotations. So we'll see in a bit what a program looks like, but these annotations, they help to specify which part of the code is going to run on the CPU and which on the GPU, and so on. So it extends the C++ programming language. It has more than that. It's also a runtime environment, meaning like it has its own compiler, which is called the NVCC compiler, and it has its set of libraries, and also it has the device driver, the GPU driver. So taken all together, we think of it as a runtime environment, which we call CUDA. Now, in case of the GPU, one can even say that CUDA is actually a co-design between the GPU hardware and software. So the software has been designed in a way that maps onto what the hardware looks like. And even the hardware has been, to some extent, designed in a way so that it becomes easier to program. The greatest advantage of CUDA is that it makes programming the GPU much easier than the time when it was not there before. We are going to write our CUDA programs in C++. Another option could have been Python. We chose C++ because it makes the systems level details more transparent, and that's what our objective is, to understand the system level details in quite well. So for instance, explicit memory management, which we have to do when writing C++ code, it will make it more clearer about a major source of latency when using the GPU. Whereas a lot of these things can get hidden away when working at a higher level, when writing the kernel in Python. So CUDA in C++, it maps much more directly to what the GPU hardware looks like. Having said that, it's still useful to be able to write CUDA kernels in Python because it makes the prototyping faster And for that, we make use of what's called the NumPy compiler. And I'll provide a link to it on the course webpage. So when thinking about GPU, what we're actually looking for is data parallelism. And it's this idea that we are performing the same computation on multiple pieces of data. Now, here we have an example of vector addition. So I'm doing the same plus operation on each element of vector A and B to get the corresponding element in the out vector. So I can apply the plus operation independently here. And in this case, if I think of each thread doing one addition, all the threads, they can act independently without having to collaborate. And it's a very obvious case of how to parallelize. In this case, how do they parallelize this? It's really obvious here. And these kind of applications where the threads can act independently without having to cooperate, these are called embarrassingly parallel computation. So vector addition is an example of that. Another example of that is converting an RGB image to a grayscale image. So in this case, on each pixel, we take its RGB values and we can apply an operation somewhat like this. So if we think of mapping one thread to each pixel, so all the pixels, they can apply this operation independently without having to cooperate. And even here, it's an example of an embarrassingly parallel computation. Not all computations are so simple. So there are cases when threads have to cooperate to get the final result. And there are cases where we want to run something on the GPU, but there's not a straightforward way of converting that computation to like parallel computation over threads. So for instance, some computations called reductions, they involve, for instance, taking an array and summing up all the elements on it, or maybe taking an array and finding the maximum over it. A lot of computations which are described by recurrences, how do we operationalize on the GPU? That needs a bit more thought. We aren't going to consider them here because it doesn't come up that often in machine learning. But for general purpose applications, there are what's called parallel primitives. To think about those primitives actually help us look at a general computation, even if it has recurrence, and then give us a way to how to formulate it in a multi-threaded manner. So any computation which we want to do, if we look at it, it has some parts which are inherently sequential, and CPU is good for that. Yeah, we don't think about the GPU, therefore the sequential portions, but some parts can be parallelized, and that's where we want to bring in the GPU. Our computation which we want to do, it's a combination of these sequential parts and the parallel parts. And for the parallel part, we have a grid of threads which does that computation. And then the serial part runs on the CPU. Now, the CPU, we use the terminology host there. So host is the CPU, and we'll see we use the terminology called device for the GPU. And this also introduces another way of looking at this program. So we can think that there's a main control program running as a process on the CPU, and at different points it launches job on the device, which is really a co-processor. So a GPU, it's a device, and specifically it's a co-processor here. So the main process running on the CPU as a process. So the main process on the CPU, it launches jobs on the device and so on. In its lifetime, the process can launch multiple jobs on the GPU. And these jobs are self-contained, which means that the CPU process can give the job to the GPU and carry on. So it doesn't really have to it doesn't have to stall, the process doesn't have to stall for the GPU job to get completed. And there is the GPU and the CPU in this way can act in an asynchronous manner. Now the grid of threads which get executed by the GPU, They are organized in a two-level hierarchy for reasons we will see shortly. So the threads are organized in blocks, and the grid is a collection of blocks, and all the blocks, they have the same size, meaning the same number of threads. Usually the blocks have sizes between 128 threads to a maximum of 1024 threads. If you have more number of threads than 1024 in a block, the GPU might complain. So there's an architectural limit to what can be the maximum block size. Usually we take a default value to something like 256, but this can be tuned. So here, this thing, by this symbol, I'm indicating an individual thread, and all these blocks, they make up a grid. So the question arises that why did we have to organize the threads in a block, and what sort of concept does it introduce? Before that, we see, so here, when we thought about grid, thread, block, and grid, we had programming abstractions in mind, and this figure, it shows how it maps onto the GPU hardware. So the GPU is an array of execution units called the streaming multiprocessors, and these are on chip. Off chip, there is what's called global memory or high bandwidth memory, and these are connected via a bus. So now on an 800 GPU, we have 108 streaming multiprocessors, and each streaming multiprocessor, it executes a block. So thread blocks get mapped onto these streaming multiprocessors. And so this is really like the physical link. And each streaming multiprocessor can execute a few blocks concurrently. Okay. So let's say that we had a grid of threads to do whatever work we wanted to do. Here, let's say we wanted to convert this RGB image to grayscale. And here we can see that we took our grid and actually had a 2D division in terms of blocks. And then we assign these blocks to streaming multiprocessors. And at a time, each streaming multiprocessor can be assigned a few blocks, but not a lot, because the blocks, they take up resources on the streaming multiprocessor, which is quite limited. But the grid can have many more blocks than can be accommodated on the streaming multiprocessor at a time. So the rest of the blocks, they wait in a queue, and then the block scheduler schedules them as and when the streaming multiprocessors become available again. Now, blocks contain threads, and when a block is executing on a streaming multiprocessor, we are guaranteed that all the threads in a block, they are scheduled simultaneously. Whereas different blocks, they usually cannot communicate, and they can get executed in any order. So here, although we see a nice arrangement of these ordering of blocks, but really there's no guarantee in terms of how blocks get scheduled. So what this means is that if cooperation among threads is required, it has to happen within the blocks. So all the threads within a block, they can cooperate with each other, maybe share memory and so on. Whereas the blocks, two blocks, they are in a way independent, and they can be scheduled independently on the streaming multiprocessor. Now, the reason why this helps having this concept of dividing the grid into a lot of blocks is for this reason, that let's say our grid has 8 blocks and we want to execute it. So the concept of having blocks, because these are independent and they can be scheduled independently, it provides what's called automatic scaling or transparent scaling. So if a GPU is not so powerful, it might have smaller number of streaming multiprocessors. And in that case, the blocks might take longer to run. Whereas if the GPU is more capable, is more powerful, and has a lot of the array of streaming multiprocessors is quite big, then one can run through these blocks in the grid faster. So because we know that the blocks are independent, so they can be scheduled based on how much availability is there of the streaming multiprocessors. Now, one thing to keep in mind is that this scaling up, it's automatically done by the CUDA runtime. So it takes an executable which specifies that we have these many blocks in the grid and so on. and it queries whatever GPU is attached to the CPU. It queries and knows how many streaming multiprocessors are there, and then accordingly it can schedule things within the GPU. So that's fine. And here we have another observation that as GPUs become more powerful, what really happens is that the array of streaming multiprocessors that becomes bigger. We have many more number of streaming multiprocessors as the GPU architecture evolves. But individually, each streaming multiprocessor, it doesn't become very different from its previous generation. So for instance, each block has a limit of 1024 threads, and that's been the case for quite a while now. And this scaling up of the GPU by adding more number of SMs, it's what is called scaling out. And that is opposed to if we wanted to make the GPU scale by making these individual streaming multiprocessors bigger and more capable. And the reason for that has to do with the fact that what GPU is aiming for is massive parallelism. So if I were making the individual units more complex, bigger, I would be leaning more towards the CPU, which we don't want to do. Instead, for the GPU, we want to have a large number of these units, which individually they might be simple. So that's okay. So let's look at CUDA program to do the vector addition. Now, vector addition is the simplest example we can start off with. It's like the hello world of CUDA. But looking at this example first will help us understand the syntax of CUDA and its basic structure. So let me pull up this code. So the first thing which we see is that this file has the extension .cu, which says that it's CUDA code. And if we look at it, we see that by and large it is C++, or rather it's resembling more C here. But then there are some extra annotations, and these are the extensions provided by the CUDA. So here we have three functions, and for the third function here, it's annotated by global, and this is a way of specifying that this is the GPU kernel. So threads on the GPU will run this code, whereas these other ones, which don't have any annotation, they could have had __ host __. But if it's not there, then it means it will run on the CPU. So the CPU will really start here in main, and it will allocate two arrays of some size, and it will it's populating them here by some values, and it's calling this function, which will be responsible for calling the GPU kernel, but it does actually three things. So we are working with C++, and first we have to allocate memory on the GPU to hold the two input arrays X and Y, which are now present on the CPU, but they need to be copied on the GPU. So this is part one, and this is happening by means of here CUDA malloc. So I reserve space for X and then for Y. Now here we have separate pointers, so which point to memory in the GPU where this space got allocated. If we try to dereference this pointer here within the CPU code, we will end up with an error because this pointer really holds for on the GPU memory and not on the CPU memory. And once we have allocated space on the GPU, then I can instruct CUDA to transfer X from the CPU to XD on the GPU, and I have to tell what size of the array am I looking for. This is a constant which says that, so here the first argument is the destination and the second argument is the host. So it's saying what's the nature of the destination, which is device, and the source is the host, and so on. So the interfaces, like CUDA malloc looks very much like malloc, and CUDA memcopy has this constant so that we need not have two functions to copy data on either direction. We can just use that same function with different constants. And then we invoke the kernel, and we see that when it looks a bit like calling an ordinary function with some parameters, but there's something here, and this basically tells what the grid looks like. So it helps us specify the organization of the grid, and this is called execution configuration. So in block size, I'm telling how many threads should be present in each block, And here I've taken it to be 256, which is not a bad default size. And then the number of blocks would be basically like this, how many total elements are there in the vectors, each array, what's its length, divided by the block size of each individual block. So if my grid has these many blocks, then I'll cover all the computation which we want to do. Now notice that here for the number of blocks, I did a ceiling operation, and that's because it might be that the array size is not perfectly divisible by 256. So we might need to have a separate last block which will act on the last few elements of the array, and some of the threads in the block might not do any work. And once this kernel is called, then the CPU comes here and it copies the result which is contained in YD. So here YD is holding XD plus YD, each coordinate, and it copies the result from the GPU to the CPU, and then it finally frees up memory which we allocated on the GPU. At this point, what's really happening is that a grid of threads is launched, and each thread, it starts executing this particular function which we have here. So it starts executing this. All the threads execute the same function. Now, if that's the case, then how can we ensure that each thread, it acts on a different piece of data? And so that is done by giving each thread its ID. So each block has its ID, and each thread within the block has its own ID. So in this case, the thread IDX, block dimension, block IDX, these are built-in variables that's provided by CUDA. So each thread can access this and get the right value for itself. And we can take all of this together to get the individual ID for each thread. Now I'll come to the reason why these look like structs and they have the X attributes in a moment. But block dimension is basically saying how many threads are there in a block, in each individual block, and block IDX is saying that for this particular thread, in which block is it placed. And thread IDX in this case varies from 0 to 255 in each block. So each thread has its own particular int I variable, and this is private to the thread. And that's why it knows, using this, it knows which array index to act upon. And I had this boundary check here because we did consider a case where the number of elements in an array might not be perfectly divisible by 256. So for the very last block, I want to ensure that only some of the threads, they do the computation and the rest they remain idle. If they don't remain idle, then they might make illegal memory access. Okay, so far so good. Maybe we come back here. So moving on from vector addition, which was a trivial example, to an example which I'm more interested in, which is matrix multiplication. It occurs a lot in our machine learning applications. And interestingly, it's one of those computation which can take good advantage of the GPU. We saw last time that if the matrices are large enough, then it can be in a compute bound regime. So let's look at the matrix multiplication computation and see how we can map it onto threads. When multiplying two matrices, A and B, and here we are assuming all to be square matrices for simplicity, n by n, and C is the output matrix. So the ijth element in the output matrix, it is like a dot product between the ith row of A and the jth column of B. And the way I will map the threads in a grid to C is basically each thread is corresponding to one coordinate of C. So each thread is responsible for computing one element in the output matrix, which means that each thread is in a way doing its own dot product. So here as well, we see there is the way we are formulated it. It does seem the threads, they can behave independently without having to cooperate. Let us see that this is not the best application. It has efficiency issues, but for the time being, we'll stick with this simple implementation of matrix multiplication. So for the vector addition example, we considered a one-dimensional arrangement of threads and blocks. But now we have matrices, and it's easier for us if we think of the thread and block arrangement as two-dimensional. So the whole matrix here, I have partitions. So the whole matrix is like a grid. So because each thread is corresponding to a coordinate of C, so the entire grid, all the collection of threads is the entire C. And I can tile it up in a 2D fashion by these blocks. And each block I can, here I've shown a toy example, but there'll be usually many more blocks in the grid. And each block would be a 2D arrangement of threads. So it depends upon us, like CUDA, it lets us organize threads and blocks in 1 dimension, 2 dimension, and 3 dimension. And the nature of that organization depends upon what kind of data we are working with. So for instance, with an array, maybe a 1D array element is K. With images, it's more natural to think of 2D arrangement of threads and blocks. And let's say if there is some molecular simulation in space, maybe voxels, they map better onto 3D arrangement of blocks and threads. So I'll come to this indexing in just a moment, but let's start off with looking at the code for the simple matrix multiplication. And here as well, the main is basically allocating space for the two input arrays. Here I call them X and Y, and also for the output matrix. It initializes the input matrices and then calls this function, which is doing the 3 parts which we saw in vector addition. And so the part 1 of this has to allocate space on the GPU to copy the input matrices and also create space for the output matrix on the GPU. And again, like we have by _d, we want to say that these are pointers to matrices on the device, on the GPU. And then we copy the input matrices from the host to the device. Now then we do launch a kernel here, we give the parameters, but the execution configuration is now, it says that the threads and blocks are arranged in a 2-dimension fashion. And this we do it by a variable of type dim3, which is provided by CUDA. And here we see that the blocks have block size by block size threads. In general, it can be 3D, but for us, we keep this last dimension 1. And these blocks, they make up the grid in this way that we basically divide each dimension. These are square matrices, so we divide the dimension of the matrix by the block size. And here what's happening is it's the same seeding operation. So it might be that n is not perfectly divisible by block size. So I might need to have an extra block that covers the remaining elements in n, and it's the seeding operation. And similarly, I say that my grid is basically grid size by grid size. And I pass these as the execution configuration. And after the kernel is done, then the resulting output is copied from the GPU to the CPU, and then we free up whatever memory we allocated on the GPU. Now, when this kernel gets executed, the grid of threads, they get launched, and each thread, it executes this particular code, the same code. It works because each thread is able to know which piece of data, which output coordinate it has to obtain by means of these built-in variables which are provided by CUDA, and they are different for different threads. So each thread can query which block am I a part of, and within this block, what is my thread ID. And we can combine these together to get the row and column of the output matrix which it has to act upon. And once it knows that, then it can do the, so once a thread knows that it's responsible for getting this, then it can do the respective dot product, and that's what we show in this running sum here. So this part is computing the dot product, and so here we are checking for the boundary condition because we saw that, like, we're considering the case where the shape of the matrix might not be perfectly tiled by the block size. So we might need to have some extra block. Okay, now let's look at a bit more closely at how the thread knows which element of the output it has to obtain. And the way to think of this is that the block ID X is a struct, and it has, in this case, it has two elements, X and Y. There's also a Z, but that's equal to 1. And now each block, so for instance, this block here, its block ID X dot X is 1, but its block ID X dot Y is 0. So IDX dot Y is indexing the row, and block IDX dot X is indexing the column. And within the thread itself, it's similar. The thread IDX dot X goes in the, it spans the columns, and thread IDX dot Y spans the rows. And a thread can know that what is the dimension of the blocks by these block dimension built-in variable with its attributes X and Y. And in our case, they are both equal to block size. So the thing to note here is that X, we are usually used to thinking of X indexing the rows and Y indexing the columns, but CUDA does it a bit differently. And once we have that, once we know that, then I can get the row. Just, it's like an analog of what we did for vector addition. And similarly for the columns. So that's fine. Maybe then we can analyze this algorithm a bit. We will look at the profiling results for all the code which we are seeing here for the matrix multiplication on the profiling tools provided by NVIDIA in another video. But here, just by doing some napkin calculation, we can arrive at some conclusion. So in our implementation, in each loop iteration, So in each iteration of the loop, we did 2 loads of floats, which are 4 bytes each. So we loaded 8 bytes of float. And then we had in each iteration 2 flops, one for multiplication and one for addition to the running sum. Now, assuming that that n is large enough, we can maybe ignore this last store. So we are reading 8 bytes in each iteration and by doing 2 flops. So overall, the arithmetic intensity of our implementation is 2 by 8, which is 0.25 flops per byte. Now, a modern GPU like 800, that its tensor cores, so because we are doing matrix multiplication, we are looking at tensor cores, and we're looking at the value for dense matrix multiplication. That's something like 1.56 teraflops per second. And its peak memory bandwidth is so much, which gives an ops byte ratio of 100, which means that for every byte coming in, if we do 100 flops, it is then that the GPU will be kept fully utilized. And we are much short of that. So we are 0.25% of this ops byte ratio, which is much, much less. And so the conclusion which we have here is that we are severely memory bound in this particular case. And just like many other applications which we'll encounter, we are limited by memory latency and the throughput limitation. And so what we need to do to make our implementation better, to get somewhere near this ratio, although it will be hard to fully get here, is to improve our memory access patterns, because that's really the bottleneck. And to get there, we can make a few observations. Let's look again at what we have been doing in the matrix multiplication implementation. So consider a particular block in the matrix C. So we tiled initially, in our example, we tiled the output matrix with blocks. And there we saw that each thread is responsible for obtaining one coordinate of the output. Now, from the perspective of one block here and the threads within that, let's see what's going on. So each thread is doing a dot product between a particular row of A and a particular column of B. And overall, the threads in this block, they are acting upon this particular region, shaded region of A and the shaded region of B. Consider 2 threads in this block, P1 and P2. They have the same row but different columns. And when doing the dot product, they are working with the same row of A but different columns of B. Similarly, consider threads P1 and P3. they have the same column in the output matrix C, but are on different rows. And they are working with different rows of A in the dot product, but with the same column of B. So looking within a block, we see that the threads are in reality working with the same piece of data to some extent. And this gives us an idea, because what really is a challenge for us is that each thread is reading all this data, and the way to maybe visualize this is think of A and B as huge, very big. So over the course of a thread's lifetime, it's reading in all this huge row and all this huge B. And all the threads in a block, they are doing all of this without being aware that there are other threads with which they could have shared the information which they read in. Because the global memory is slow. So it has high latency, and reading from the global memory, it's an expensive operation for the GPU because the compute units are so fast. So if a thread is spending all that effort in reading data from the global memory, why not share it with other threads in a block? So to be able to do that, we need some support from the hardware. And the thing which first comes to mind is cache. So on the CPU as well, tiling for matrix multiplication is an important concept, where we make the matrix multiplication more efficient by improving its memory access, by improving the locality, so that there are a lot of cache hits, and in that case, like, we don't have to return to the RAM to read everything. It's not very different on the GPU as well. The GPU, if we refine our picture a bit, is streaming multiprocessor. It has these small cores, and there are lots of them. These are called, each of them, it's called GPU core or streaming processor. And along with that, it has a memory called, it's memory meant for the registers, and a memory called the shared memory. So registers and shared memory, they are individual to each streaming multiprocessor, and they are on chip. On A100 GPU, there are about 64 of these cores per streaming multiprocessor. And here's the interesting bit, that the registers, there are a huge number of them, about 66,000. And it's very different from the CPU. So the point of the registers is that the threads, as they're executing, they will store their intermediate states on the registers. And here, now on a CPU, we have much fewer threads. There are about 32 registers, sorry. So we have about 32 registers on a CPU core. And here we see a big difference with the GPU, that GPU has an enormous number of registers, and there we have hinted at why, because the GPU is based upon having a large number of threads executing in parallel and being present together. It's important that if some threads are waiting for something to arrive from memory which has high latency, then we don't stall the compute unit, but rather we schedule some other waiting threads and so on. And this is really the idea of latency hiding, and this can only work when the context switching between the threads is super fast. And for the GPUs, in fact, it has zero overheads, because there are so many registers that when a thread is put from running to sleep, its state, it can remain in the registers and it doesn't have to be transferred to some main memory. So that's the reason why we have this much amount of registers per SN. And we have about 164 KB of shared memory on the A100, which says that it's not a lot. So we are going to use shared memory as something. So shared memory is basically all the threads within the block, they can access the shared memory. So they can put data in the shared memory, which other threads in that same block, they can use. Threads, let's say if two blocks are scheduled to the same multiprocessor, threads in two different blocks, they cannot access that same data kept in the shared memory. So it's really per block shared memory. Here I have not shown the L1 and L2 caches, but those are also present. So now, with the knowledge that GPU provides us shared memory, what can we do? So what we can do is we can maybe, well, we can think of loading this entire region of A and entire region of B in the shared memory, and then the threads in the block. So once these have been loaded, then the threads in the block, they can act upon them. Now, one thing I forgot to tell you is that both registers and shared memory, they're super fast. They have like very low latency and they have very high bandwidth. So fetching anything from shared memory, it doesn't cost much as compared to what price one has to pay for global memory. So once these are present in shared memory, all the threads can access all of this super fast, and our memory, the figure which we saw last time, it will become much better. The challenge really is that we see that shared memory is limited in size to 164 KB. And if A and B, they are big, then it won't be possible to load up all of this region here and here. And instead, what we can do is we can load a part of A and a corresponding part of B, we call them tiles, and then loop over those tiles. So in this way. So in each iteration, I consider one tile of A and one tile of B. And then all the threads now, once they have been loaded on the shared memory from the global memory, they try to do whatever they have to do with these tiles. And in a way, if you think from the perspective of D, what it's going to do from the perspective of P1, it's going to look at this row here in the tile and its respective column in the tile and get, maybe we can call it a partial dot product. And once the tiles have spanned this entire region, so all the columns for A and all the rows for B, then we would have accumulated the full dot product for B. So this is the idea behind tile matrix multiplication, and this helps us improve memory accesses by in a way making much fewer memory read requests to the global memory, bringing things in the shared memory, and then all the threads working with that. So in a way, this has what's called high locality or implementation, and as we'll see in a bit, it improves the performance quite a bit. Here I wanted to show again like the refined memory hierarchy. So each thread has its own registers. It might also be worth saying that the set of registers here, they are for each kernel, they are dynamically partitioned among the threads, meaning that it might be that a particular kernel requires each thread to have 8 registers, another kernel requires it to have 16 registers, and so on. But on the CPU, it's different. On the CPU, every time a thread is running, it has access to all the registers, which may be 32 or something like that. So there's a dynamic nature to this register memory. Now, all the threads within a block, they can share anything kept in the shared memory. So that it's all block. And then there's the whole grid. It has a collection of blocks. And the blocks, all of them, they can access the global memory. Okay, so with this, let's look at the implementation of tile matrix multiplication. And really, it's only this function, the kernel, which has changed here now. Even here, what remains the same is that each thread knows its particular row and column it has to act upon. What is different here is that each block is allocating space in the shared memory, and here by means of this annotation, it indicates that this thing should go in the shared memory. So the space for a tile of A and a tile of B, and in each iteration we are going to read a tile from the global memory to the shared memory. Now, an interesting thing to note is that although each thread is executing the same code, this allocation, it happens only once per block. So not once per thread, but once per block. And this is where we iterate over the multiple tiles, over all the tiles. We didn't do boundary checking here, but one should. So we will we can have a boundary check here. If row and column are less than n, then we proceed. Now, there are two phases to this. I go back here. So there have to be two phases to working with these tiles in each iteration. In the first phase, each thread is responsive. So note that the tile size, it's useful if it's the same as the block size. In that way, each thread in the block, it can be responsible for loading up one particular corresponding A element in the tile and one B element in the tile. And if each of the threads do that, then the style of A will get loaded, the style of B will get loaded. But before the threads can then start doing their own partial dot products, there has to be a sort of synchronization among the threads at this point. And this is because in this particular instance, the threads are cooperating, they are working together. And going back to the code here, so once each thread has done its job of loading its respective element in the shared memory tile, it has to wait for the slowest thread in the block to catch up. And once all the threads in the block, they are done loading the respective element in the tile, only then do we proceed to compute the partial dot product in a way. And this makes sense because otherwise, let's say one thread is fast to load up its respective values and it moves on next to computing its partial dot product, but the values present in, like, it makes use of values apart from what it loaded, and they can belong to some previous iteration because the respective thread was not fast enough. So for this point, we need to ensure that A and B have the right data before we move on to computing the partial dot product. And even after that, I need to synchronize the threads so that we are sure that each thread is done with computing its partial dot product before, like some other fast thread moves on to its next iteration and starts like loading its data in the tile. So there has to be an aspect of cooperation, like synchronization in the threads when working with having cooperating threads. And we do this by means of this function, which is called sync threads. It's what's called a barrier synchronization. And this is really a way of ensuring that before I move on, all the threads have reached up to this point. So that's another concept which is introduced by the tile matrix multiplication. We do see like the tile version of the matrix multiplication. We'll see it in the profiling video. It does provide speed up between something like, so it reduces the execution time to maybe 20%, 15 to 20% of the original live version. It's only one of the ways of optimizing the matrix multiplication operation. In real libraries like CUDA and so on, which are provided by NVIDIA and which are actually used for matrix multiplication by PyTorch, the libraries are heavily optimized. They have other techniques as well, apart from tiling. And like the focus of some of those techniques is really how to improve the memory accesses even further. So that's it for now, and I'll see you in the next lecture. Thank you.